Hello everybody, I am Melvin Wolf, and my co-author is Professor Dr. Jürgen Schönwälder, and in this video I'll try and summarize the key points of our paper applying metamorphic testing to homomorphic cryptography. We will quickly go over our findings from our survey of metamorphic testing, then go into applications of metamorphic testing to security in the past, quickly explain what homomorphic cryptography is, quickly explain how you can abstractly generate test cases or tests for homomorphic cryptography. Then I will show what Palisade really is, and finally we will come to the metamorphic relations we used, the results we found, and finish with a short conclusion. So really there were two main takeaways from our survey of metamorphic testing, which we found to be relevant for our paper, or highly relevant for our paper. The first was MR composition, and that's the idea of creating new metamorphic relations by combining two or more existing ones, and thus being able to verify what each of them does in a single execution. The other was the concept of test case diversity, which tended to remain somewhat vague and has a couple aspects. So first there's diversity, or difference, if you so will, of the paths executed by the source and the follow-up test cases. The idea being the more different the paths are, the higher the chance of finding a bug. Second, there was a concept of diversity of sets of metamorphic relations used to test a single program, with a key finding being that a small set of highly distinct or diverse metamorphic relations is likely to find more bug than a high amount of metamorphic relations which are all similar to each other. However, one has to note that diversity was judged subjectively, which is something which would be great if it could be changed. And then finally, there's a concept of diversity of test case inputs, which is less of a metamorphic testing specific thing, but rather comes up all around testing in general, especially random testing. So, how has metamorphic testing been applied to security in the past? First of all, there's one paper by Chen et al., which tested code obfuscators, and they used four metamorphic relations. I'm just going to present one of them, which is that for any program P, if you obfuscate it, obfuscate means making the code unreadable while keeping the same functionality, then P prime, the obfuscated version of P, and P prime prime, the obfuscated version of P prime, all three, P, P prime, and P prime prime, should remain functionally equivalent. Maybe more relevantly, metamorphic testing has also been applied to cryptography in 4 or 5 papers, namely to RSA, SHA-3, triple DES, the Hill algorithm, and to candidates for quantum-resistant cryptography. And some of these papers were trying to find live bugs in either implementations or candidates, while others were trying to assess the effectiveness of metamorphic testing in these contexts, and hence were using mutation analysis. So I'm going to present some of the metamorphic relations that were used, or even the majority of them, because there actually tended to be quite a high repetition between the papers, which is quite understandable, I think, if you consider that the functionality provided by a typical encryption scheme is simply limited. So the first and maybe most basic test is that if you encrypt a message M and then you decrypt it again, you should still be having the message M. The second metamorphic relation focuses on second preimage resistance, which says that the encrypted version of a message M should be very hard to reproduce by encrypting any other message which is distinct from M. And so to test this, or one way they tested this, is to modify one bit at a time of M and encrypt it, and simply verify that all the encrypted outputs are distinct of each other, and thus verifying that flipping a single bit is not sufficient for an attacker to create a corresponding equal output. Third of all is the opposite of the previous test, if you so will. Namely, if you give a software a message M, or a string M, and the length n of M to be encrypted, then only those first n bytes or bits should actually be affecting the output. And so to test this, we can simply flip individual bits beyond n in M and verify that the output does not change. Finally, in SHA-3, there is a functionality to compute hashes either in a single step or through multiple steps using a update. And well, either way, the hashes should stay identical, and that is the metamorphic relation. So, what is homomorphic cryptography? It's based on a basic but quite amazing concept, namely, wouldn't it be cool if we could operate on encrypted data? And it would be cool indeed, because it would allow us to do a lot more operations, or do the same operations we already do on privacy-sensitive data, while absolutely guaranteeing that privacy is guaranteed. And so with that as a motivation, homomorphic cryptography implements homomorphic mapping between the plaintext and ciphertext spaces through the encryption and decryption functions. Any homomorphic cryptography scheme makes it possible to perform at least one type of operation on the encrypted data without access to the underlying plaintext and without the key. If a homomorphic scheme supports at least two different operations and an indefinite depth of these operations, it is called fully homomorphic. So, how can we design test cases for homomorphic cryptography? And this will be on the abstract sense. Well, the most basic test, since it's still cryptography, is the encrypt-decrypt test we already just talked about. But maybe we can augment this test quite easily by simply performing some homomorphic functionality. So we could perform an operation on M as well as on the encrypted version of M, and again verify the outputs are equal. We could then maybe say we want to increase diversity, and instead of performing one operation on both sides of the equality, we could actually perform distinct but equivalent operations. So in this example, adding M to M and multiplying M by 2, assuming that M represents a number. Another option is to simply increase the depth of operations. However, if we want to go one step further, we can perform the same operation but in different ciphertext spaces. So by that I mean either using different homomorphic encryption schemes, different implementations thereof, or simply different settings and environments for the same scheme. Finally, we could combine these ideas and perform equivalent but distinct operations, such as we just talked about below, in different homomorphic implementations. So overall, we can say that really it's not actually difficult to find metamorphic relations for homomorphic cryptography, which is not always the case with metamorphic testing, and hence the difficulty actually shifts to evaluating and deciding which ones are best and you want to use. So, what is Palisade? Palisade is a lattice encryption library written in C++, and it's supported by DARPA and developed by a consortium of universities, think tanks, and companies, including MIT and Raytheon. It implements the BFE and BGB schemes along with some subvariants thereof, which are fully homomorphic schemes for integers. Furthermore, it implements CKKKS, a fully homomorphic encryption scheme for real numbers. However, in the implementations, the user has to define which depths of operation he wants to be supported, and hence, since this cannot be infinite, they are actually only somewhat homomorphic encryption scheme implementations. Palisade also has some further functionality, but that is out of the scope of this paper. These numerical schemes can take either a single number or a vector of numbers as an input. The main operations supported are addition, multiplication, and subtraction, and those are the ones we focused on in this paper. In Palisade, the way it works is you first have your native C++ type, so maybe an integer. You encode that into a Palisade plaintext using one of three different types of plaintext encodings, and then you can encrypt the Palisade plaintext into an encrypted ciphertext. So, what metamorphic relations did we end up using? First of all, we started with the rather obvious decrypt-encrypt test, but we added an identity operation. So that was randomly picked for each execution as being either one of x times 1, x plus 0, or x minus 0. Additionally, we always generated the input m randomly within the bounds given by Palisade. Then we have MR2, which is that for any m, we would expect that the square of m is equal to the square of m in the ciphertext space once decrypted. However, the idea here was actually to force overflow errors, because if you square a number within certain bounds, then the probability that the square of that number will exceed those bounds is high. And this is what we were aiming for here. However, MR2 actually led to a different discovery, namely that a certain comparison operator between plaintexts was not implemented. And so, well, MR2 failed for every implementation, but also that was the first bug we found. So to fix that, instead of using basic plaintext of Palisade as a base type, we switched to using native C++ types, and hence after decrypting we also decoded back to native C++ types, hence allowing us to do the comparison. And actually the majority of the schemes we tested failed this metamorphic relation with overflow errors. So then we decided to take it one step further for those that failed MR3 and find out whether the overflow errors were limited to the multiplication or whether they happened anytime there was an overflow, so to speak. And for that we decided to force overflow with addition. So we took out the random input, simply set m to be the high bound, and then added it to itself. And actually the result ended up being -1 in each of these cases, which strongly hinted at it indeed being an overflow issue. Finally, we have MR5, which we decided to use for those schemes which actually did pass MR3, and we wanted to see if we can somehow force overflow issues anyway in some way or another. And so to do that, instead of just squaring once, we multiplied m with itself x times. So what are our results? In the second column you can see the three different encoding types. CKKS only supports plaintext, so that's why there's only one of it there. MR1 was passed by every metamorphic relation. MR2 was, as we discussed, failed by every encryption scheme. MR3 failed for the majority of the BFV schemes, and for all those which failed BFV, MR4 also failed. And then finally, MR5 was only passed by CKKS, so CKKS was the only one which consistently threw a valid error when getting overflow errors, while BFV RNS and BFV RNS-B with an integer plaintext started failing after a multiplicative depth of 5 was reached. And at that level, roughly 10% of test cases failed, but once we went beyond a multiplicative of 5, failure was consistent. So, overall, as a conclusion, I think the main takeaways are that metamorphic testing definitely can help assure the quality of homomorphic encryption schemes, because to me at least it really feels like this testing and this encryption scheme just kind of fit each other, which may have something to do with them both having morphic in the name. And furthermore, it is very easy to generate metamorphic relations for homomorphic cryptography, or to combine existing ones into new ones, and so on. And so I hope that by continued research in this general area, this might actually help us in defining and metricizing the concept of diversity, for example, or automating the process of picking the best metamorphic relations, or the best sets of metamorphic relations. I really think there's quite some potential here, and I would hope to see that there is some progress in the future. I hope you will excuse me for not adding references to this presentation, but I wanted to keep it short. Thank you, and see you in the Q&A.
Well, hello everyone. Welcome to the last session of the workshop. In this session, we will have 3 talks. The first one is the one that you just attended by Melvin Wolf, who presented his work on applying metamorphic testing to homomorphic cryptography. At this point, you probably should be familiar with the procedure. You have to write your questions in the chat, and I will ask those questions verbally. Okay, don't be shy, far away. Ensure that you have many interesting questions. We already have one from Alistair Donaldson. Basically, he asked, whether did you report the bugs you found and were they add on?
So yes, I did report the bugs. I simply filed a bug report or an issue on GitHub. And yes, they were acted on. So they said thank you, and they said it's a bug, and then they fixed them a couple months later, one after the other. So yes.
Okay, thank you. Please, again, don't be shy. Fire away. Okay. In the meantime, I will ask my questions. I have a few myself, but don't be afraid of asking. Yes, well, Melvin, the metamorphic relations that you propose are, it seems to me, I got the impression that they are quite program specific. They are specifically designed to test the Palisade features. My question is, how reusable do you think they are? Could those be applied to others, to similar tools?
Yes, I think so.
Yes.
I'm a bit surprised. I would have thought that they are applicable to all homomorphic cryptography systems. Maybe with some minor changes depending on the implementation. But from the overall, well, maybe not the overflow testing. Okay, so the overflow testing, I agree. But no, I do think they're rather applicable because you always going to have this question of overflow and how you handle it. Now, you might not have issues there, so then maybe going as deep down that area won't have any purpose because you would just notice that overflow is handled correctly. So I guess, yes, now that I think about it, like half-half. I think they are somewhat transferable, and at least, or especially the core concepts I explained about how to design and use and so on is very transferable. The specific relations may be a bit less.
Yes, actually, that was exactly my feeling. I mean, in first, you explained some general ideas that I think they are quite reusable. I totally agree with you. But then you present very specific metamorphic relations for Palisade. So my question is, have you considered defining those general ideas as metamorphic relation patterns? You know?
I understand what you mean. So the way it actually came about is that and that's maybe also why the metamorphic relations are not as perfect as they could be, or however you want to say that I first came up with the metamorphic relations and the testing, and then actually the general concepts more came after, when I understood what I had done and what I was doing and what you could do with this entire environment, because I was new to both homomorphic cryptography and somewhat metamorphic testing. So yes, have I thought about it? Not really, but it makes a lot of sense because, yeah, it is going in that direction, right? And it's very possible to do thanks to the. Well, I don't think it would be too much work, so it makes a lot of sense, and I will consider it.
Okay, great. There is another question from Alastair. Can differential testing be used as an alternative way to circumvent the Oracle problem in this domain, using cross-check multiple implementations of an input?
So I don't know differential testing. I'm trying to understand on the fly.
Basically, if I understood well, it's having different implementations of the same function and then checking if the output match.
Yes, so that's actually something I talk about in my paper. Consider that a metamorphic relation. No, maybe it's not. All right. But yes, you can definitely do that. It makes a lot of sense in this context. And it is actually something I talk about a bit in my paper.
Okay, thank you. Based on your experience, Melvin, how difficult was it to come up with the metamorphic relations? Do you think that's something that a regular developer could do, or that's something that you really need an expert to do that?
Well, you don't need a homomorphic encryption expert because I'm not one. I'm definitely not one, right? So yes, I would say yes. At least any metamorphic tester should be able to come up with those. I don't feel like, yes, I did anything particularly groundbreaking or so.
Okay. Okay, well, that was on my side. Do you have any future plans in this research direction?
No, actively I don't, although you just gave me an idea with the metamorphic pattern. But my research has been somewhat on hold to my personal life, I guess.
Okay, great. Well, Alastair says, is it in a metamorphic relations? he doubts it. Let's discuss.
I understand.
Yes. Well, that's it. Do you have any other questions, guys? We have like 4 minutes left. If not, I think we can finish the session here. Thanking Melvin Wolf for his very interesting talk and paper. Again, thank you very much, Melvin, for participating in the workshop and for your contribution. Thank you so much. For the rest, well, see you in. It's really nice to see that all work on applying the implementation are being taken forward and applied to other cryptography implementations.
Yes, so I could.
Okay, yes, it's a compliment. Excellent.
No, I meant the question at the end. Right? So he says some of the MRs, sorry for kind of skipping the part of reading it, some of the MRs, such as encryption, decryption chain, should be universally applicable to all cryptographic algorithms, and I completely agree. That's basically something I realized, and why I use it as a basis, because it just makes so much sense. And basically, it's a metamorphic relation they were using without actually realizing it is one. And yeah.
Yeah, sure. That's exactly why I think they could be promoted to metamorphic relation patterns, perhaps. Okay, like something very generic that can be applied to different programs in the same domain. All right, so thank you very much again. See you guys in 3 minutes for the next presentation. Bye.
Bye-bye. Oh my God.